share my screen.
I'm actually going to steal the screen for 2 seconds.
Yeah, okay.
And let's make sure recording. And okay, welcome everybody to our 4th session now for the 2023 Building AM Design Competition. Next week, I want to remind you that we're going to have Dave from PADT as well. He's going to be talking about using the full additive advantage. So last week we heard from Haley a lot about design for additive manufacturing. And Dave is a little bit more experienced. He's been in the industry a little bit longer. He's going to dive into some of the more nitty gritty of design for additive, as well as some unique applications. Last session, we talked a lot about, throwing what you think you know about how things should look or how things should work out the window. Dave will dive into that a lot more. This week, we're talking about performing a stiffness simulation using ANSYS Discovery. I have Tyler on there, and Tyler is here with us, but Bronislav as well is here from PADT, and he'll be taking the majority of the talking during this session. So with that, we'll go ahead and just pass it over to him.
Tyler, do you want to say a few words now? Let's just start.
Yeah. So real quick, just so folks that are on the call understand, PADT is a bit uniquely positioned. We do not only simulation, we also sell and operate additive manufacturing tools and capabilities. But really the benefit that we bring is we get to go use both of those tools to really design products. And so between our team, we have about 20 or so engineers and full-time analysts that are doing this work. And this particular talk that Bronislav has put together is really focused on how can we use simulation as part of our design and why, to try to give folks a little bit more of a concept of, okay, we have these tools. How do we maybe interpret some of these results that we're getting to make a bit more detailed design decisions? And with that, I will hand that over to Bronislav and let you run with it. Thanks, Bronislav.
Okay, thank you. Can you all see my screen?
Yep, looks great.
Okay, so my name is Bronislav Piak. I'm a simulation engineer here at PADT. And today we're going to be talking about, I know the topic was kind of performing a stiffness simulation. We kind of rebranded it a little bit. We're going to be talking about structural analysis consideration. So what are the structural analysis considerations when designing a UAV? What load cases need to be considered and why? How to interpret results. So there are basically two analysis types that you want to be considering when designing a UAV. One is so-called model analysis. The second one is strength analysis, or structural analysis sometimes called. So model analysis is the fundamental dynamic analysis type, providing the natural frequencies at which a structure will resonate. Like you can see, for instance, there is a propeller, and these are some modes, natural frequencies, I guess mode shapes for this propeller. So these natural frequencies are of paramount importance in various engineering fields. For instance, suspensions are usually tuned so that they have different natural frequencies for passenger cars and race cars. So structural engineers need to calculate these frequencies for buildings, for instance, so that the seismic waves produced during earthquake do not match the natural frequencies of the buildings and they don't collapse, right? And the second type of analysis that is of importance when designing components and structures is structural analysis, right? So the simplest form of it is so-called static structural analysis. And it determines the effect of steady or static loading on a structure. And outputs of this analysis usually stress, strains, and deformations. And so they can be studied under a range of loading conditions. And this helps to identify weak areas with low strength and durability at the design stage and avoid expensive failures. So let's talk a little bit more about model analysis first. So again, model analysis is used to determine the vibration characteristics of linear elastic structures. Model analysis is also the typical common dynamic simulation for many other dynamic simulations. Basically, it's an entry point into more complex harmonic, random vibration, response spectrum, transient dynamic analysis types. But still very valuable. Again, you would always want to start with model before going deep and analyzing, these more complex types of dynamic simulations. So model analysis looks for natural frequencies and normal modes of a structure. Natural frequencies and modes are some of the most important properties of a structure, and they determine how the structure will respond. For instance, for this guitar string, what's the nature of a guitar string, right? So what's the nature of a skyscraper as a slim, tall structure? So here, well, again, why do we care about natural frequencies? The answer is to avoid resonance. For instance, here, think about the vibration of this of car when driving over a rough road. In this example, a compressor is running and the natural frequency of the piping is matching the vibration of the machinery, causing the piping to resonate. And we want to, mostly when designing, we want to avoid this. This causes unwanted noises and mechanical stress and strain, resulting in premature fatigue failure. So therefore, by knowing the natural frequency of the components, we can design them so to avoid specific ranges to prevent resonance. Here, for instance, again, why do we care about natural frequencies? To understand more complex dynamic behavior. Here we can see the wing dynamically deforming due to the random turbulence excitation. What deformation shapes can be seen? We can kind of conclude based on model analysis. Does one shape dominate? Let's take a look at what simulation of the wing can reveal. Here we can see the results of the wing and three modes presented. First, flap-wise bending mode, first edge-wise bending mode, second flap-wise bending mode. Looking at these natural frequencies from ANSYS simulation of a typical wing, we see some of the typical modes and I know what kind of excitation will be presented if excited, right? The model results can help to answer important questions. Therefore, are the first several modes expected with applied boundary condition, right? Think of the wing as a cantilever beam. What kind of deformation patterns are they representing? Is it bending? Here we can answer yes. First mode is bending mode. Second, this kind of second mode is also bending mode, but it's in plane. Then third mode as well is bending mode. Again, which mode of the wing tip is the main deformation? Is it expected? Let's consider the two systems below. One is airplane flying in the sky, and the second one is skyscraper. If an engineer plans to perform model analysis on these two structures, what will be the biggest differences despite the geometry and material differences? Well, the airplane obviously is flying in the sky. It's free of boundary conditions. The skyscraper is fixed on the ground. Therefore, if the model analysis is for a structure without boundary conditions, like this airplane, it's called a free model analysis. And it's a special kind of type of model analysis, if you will, but yeah, free, and it's actually applicable, right, for those designing a drone or UAV. Free indicates that the structure is free of loads and free of boundary conditions. The structure is free to have rigid movements in 6 degrees of freedom in 3-dimensional space. Basically, we expect when running free model analysis, we expect for this free structure basically to have first modes, so-called rigid body modes, as 3 in translational directions and 3 in rotational directions. So for a free model analysis, theoretically, the first 6 natural frequencies must be 0. You can see in this table on the left, on the right, first 6 are 0 or almost 0, right? So, and they are not completely 0 because this is due to, computer software. They have some floating point, I guess, precision. So that's why. But basically, this is 0. And starting from 7th and further, we can see that these are so-called flexible body modes. So yeah, solving the free model analysis numerically, for instance, by using finite element software, you might find the first natural frequencies, they're not absolutely 0, but should be close to. Now, why? So one of the quantitative criteria in this design competition is to design UAV such that it has so-called quote unquote best stiffness to mass ratio. Why do we care about stiffness to mass ratio? Well, without going into all the details and all the math, it turns out that natural frequency f equals to 1 over 2 pi times square root k over m, where k is stiffness of the structure in certain direction and m is mass. So basically you can see stiffness to mass ratio is baked into the formula to find natural frequency. So the trick is to balance stiffness and mass such that they result in higher value of natural frequency. Now let's perform a model analysis of this drone, let's say, right? So first thing first, let's say you have this CAD geometry that you put together while designing. You don't want to kind of, just take it and start kind of analyzing directly. So you would want to simplify first. And basically for this structure, you can tell that, yeah, the main load-bearing interface or load-bearing component is this frame. So you'd want to keep this frame. The rest you can simplify. Um, so what do we do? So, well, here we'll assume that material of this frame is aluminum. And this is, we're gonna run so-called free model analysis. So this body is not constrained in any way. Also, we created those point masses representing each motor, assuming it's 10 grams for each motor, as well as point mass in the center representing payload. Okay. And we run free model. So as expected, we see first 6 rigid body modes, and there are 0 or close to 0, right? And they're just showing how the free kind of flying object will move in 6 degrees of freedom. And then flexible body modes that you will be able to extract starting from 7. So you can see these are more significant numbers, and they represent, so this one we can call first bending mode, right? Two arms kind of in phase, while two other are kind of out of phase. This is second bending mode, all 4 are in phase. And this is third flexible body mode. This is kind of in plane bending mode, right? Now, what will happen if we increase mass of each motor? Let's say each motor is not a 10 gram, but 50 grams, okay? Again, running free model, we'll see, so this is comparison. At the top, we can see frequencies and mode shapes for when motors are 10 gram. At the bottom, frequencies and mode shapes when each motor is 50 gram. So we can see that numbers for 7th, 8th, and 9th modes actually changed, and they're smaller now. Okay, and in terms of mode shapes, they're pretty much the same, So just bending here as well, and this one as well. So why did it happen? Again, going back to this formula, we can see that. So what happened? We increased m, right? If we increase m, this made f smaller value. And that's exactly what happened. So we see 123 versus 247, etc. So now what will happen if we kind of stretch each arm, make it longer by 20 millimeters? Okay. By doing this, we kind of reduce stiffness, right? We can say it's more flexible now. Again, running a free model, same first 6 are rigid body modes and then flexible body modes comparison. At the bottom, we can see the results of the model analysis when arms are 20, each arm is 20 millimeters longer, right? So we can see again, frequencies became smaller or decreased. Why did it happen? Again, according to this formula, if we decrease K, meaning we make uh, the frame less stiff or more flexible, we decreased F. And that's exactly what happened. Okay, and that's it for model analysis now. Now let's talk about strength or stress analysis. So stress analysis is an engineering discipline based on solid mechanics. In the engineering world, stress analysis is the primary method that engineers use to find the stress and strain of a design or structure. So an engineer converts a real-life engineering problem to a mathematical model. For example, if we want to analyze a bike crank, we first need to determine the geometry with appropriate details, material properties, loads, and boundary conditions. And then, so today, solving the mathematical model is done numerically by computers with help from FEA software. This FEA software does some advanced matrix math in the background. So, and then we get the results. This enables engineers to solve much more complicated systems than was possible before. However, we must be aware that software does not do everything automatically. Garbage in, garbage out. Engineers have the responsibility to make appropriate decisions regarding numerical simulations. It's us engineers who have to decide, well, from start till very end, what are the boundary conditions, what are the loads, what assumptions we can make, material properties, and then when the results are there, it's us who will decide if they make sense, if they are what we would expect, and then kind of provide decisions and recommendations. So, I use this fancy word, finite element analysis, finite element method, also called FEM. FEM is the most widely used numerical method to solve solid mechanical problems. What it does, it takes this kind of domain and it discretizes the domain to many elements. You can see those triangles here. These are basically elements, and each element consists of many nodes. Like this is kind of representation, simplified representation of different types of elements. There could be hex elements, there could be tet elements, and you can see tet elements, for instance, has what, 4 nodes here. Sometimes it can have 10 nodes, etc. So and then kind of software operates on those nodes. It finds solutions for these nodes in the background using advanced matrix math. After the problem is solved by numerical methods, it is left to engineers' judgment to decide if the result is as expected and realistic. This requires an engineer to have a strong knowledge of solid mechanics and be familiar with the finite element analysis concepts that the software uses. And it's us engineers who have to interpret results to check the validity of the design and to find ways to optimize it. Again, software doesn't do this automatically. We'll check, we as engineers check results, we check deformations, stresses, strains, and kind of compare them to our criteria, make sure that the criteria is met, or if it's not met, what we should do in order to improve or make it compliant. Therefore, the role of engineering decision making is crucial in the process of stress analysis. Engineers need to make decisions at every step, again, from the very start, from the given initial conditions to the end results. Let's consider, for instance, this example. Before doing an analysis of the motion of the lumbar section of the spine, on the left, you can see that's kind of, let's say, that's our input. We're given some section of the spine. An engineer needs to consider these questions below and make decisions. So given a geometry file from a 3D scan of the lumbar section, which details are important and which can be ignored in solid mechanics analysis? What is the connection between vertebral bodies and the intervertebral disc, right? How one connects to two, how two connects to one, what material should be used for one, what material should be used for two, and how can we represent this complex loading condition? Where do we fix it? Where do we apply load? What load should we apply? And so on. Let's say we run the analysis next, and then we got some results. So what do we, and then we need to ask these questions. First, we need to review the results. We need to make sure that they make sense, that they're as expected. We observe here, we usually review deformations, stresses, strains, reaction forces. And then based on these results, we should kind of see and analyze. We should think about them and then decide if, in this case, if this design of the spinal spacer, is sound or it needs some changes and improvements. Traditionally, it was the engineering's role to dictate the shape of the structure. You can see that's the traditional workflow when first there was design engineer usually would kind of, create a design, 3D CAD, for instance. They would provide this geometry for, they will provide this geometry and perform themselves or to structural analysis person. They perform analysis, and then analysis will, or analysis engineer will kind of tune the geometry and provide their recommendations for design improvements and so on. Nowadays, with advances in technology, computer can help to determine the best shape. This reverse design process relies on so-called topology optimization technology. And that's where we, but again, I should say it's still us engineers who will set the optimization goals for software, but software will come up with certain shapes that are optimized based on certain targets. And you can see you all had this topology optimization basics webinar before by Jorge. So I encourage you to watch it again and kind of just to get familiar with what can be done within Discovery in terms of topology optimization. Now let's perform a stress analysis on this drone. So what are the load cases that we need to consider? First thing first, you always start with free body diagram. First load case is when drone is parked on the ground with payload and other gear attached. So you can see these blue triangles representing so-called, let's say these are legs standing on the ground. And then we have motor weight on each arm, right? Downwards, we have payload weight and some gear additional downwards in the middle. And that's it for load case 1. Load case 2, representing drone flying with payload. What we have. So again, similarly, we have motor weight, we have payload weight, we have lift force upwards, and thrust force in one direction, drag force in the opposite direction. So these are two load cases that that are applicable or important for us when designing a drone. Now, again, we start with simplifying geometry. For demonstration purposes, we will assume here that the frame is made out of plastic. We also assume, again, for demonstration purposes solely, that each motor is 1,000 gram. Point mass payload is in the center again, and it's 907 gram similarly. So this is our, I guess, finite element analysis setup or simulation setup. So we fix for load case 1 again, when the drone is parked on the ground, we fix at kind of at leg locations, I guess, and then we apply standard Earth gravity. Alternatively, we can calculate forces first and apply them instead of modeling point masses. So these two are exactly the same. They will provide exactly the same results, basically. It's just different, I guess, approaches in modeling. One when we let software calculate forces providing point masses, and the second one where we calculate forces instead of modeling point masses. And then after running it, we should review and analyze results, basically. So we look at total deformation. We can see that total deformation is almost 4 millimeters, and it kind of makes sense because, yeah, you would expect when this drone is standing on the ground, you would expect due to weight of the motors, arms will kind of deflect downwards, right? So we observe, we review equivalent stresses, and we can see that the maximum equivalent stress is at one of the legs locations, and it's 28 megapascal. Also, we can see that, again, as expected, this is kind of classic bending load pattern, if you will. You can see where the zone of high stresses is towards the fixity, if you will. So the yellowish and with some red, I guess, dots, that's where the high stresses are. Again, as expected. Whether 28 megapascal is good or bad, that's where we turn to safety factor value. And the target is safety factor should be more than 1. To put it in simple words, what a safety factor is basically a ratio of allowable stress to actual stress, like anyway in your structure. And you can see the safety factor pattern field is kind of in line with stress field, because you can see, the lowest safety factor 1.28 is at the highest stress location. So they're kind of inverse. So the higher the stress, the lower the safety factor is. But still, the lowest is 1.28, which means that we satisfied the target requirement. So for load case 1, we can conclude this design is good. Let's consider load case 2, drone flying. And here we kind of simplify again. We will neglect thrust force and drag force. We'll fix 4 kind of, I guess, arms on the outside, and we'll calculate and apply the remote force representing payloads. So we'll assume 3G vertical acceleration, which is in dynamics. So we're trying to cover kind of dynamical behavior of this drone, because you may say, well, isn't gravity is 1G? Yes, but in dynamics, G's are higher, basically, if you will. So we assume 3G, and that's the force based on 3G and mass. Okay. So we apply this boundary conditions and loads, and again, review results. Total deformation as expected and makes sense. So it'll bend in the middle, and it's 1.2 millimeters. Equivalent stress is 14.6 megapascal. Does it make sense, the pattern? Yes. So we have the fixation points on the outer arms. So it'll bend kind of this way. So yeah, higher stresses towards the fixity points, some high stress in the middle. So this makes sense. And safety factor as well. Let's see. The minimum, the lowest value for the safety factor is 2.475, while the target is 1 again. So we can conclude that in load case 2, this design is good as well. So there may be other load cases depending on the other relevant scenarios and design of your drone. So think about it, kind of, again, analyze, maybe do your research and see what can be relevant, what load cases you may have to consider. If you want to learn more about model and structural analysis and how to perform them using ANSYS software, we provided these links. Yeah, kind of, I would highly recommend to at least look at them and even maybe try. There are some workshops that are great. And there is one more link, just another good tutorial where they just kind of again walk you through the not only FEA but also CFD, computational fluid dynamics, and I think some topology optimization as well of when designing a drone. And again, using ANSYS Discovery. And that's it, I think, for me now.
Do you mind if I add like 2 more comments, Bronislav?
Yeah, sure.
So one is, you talked about going from like a more computer-based approach and going from having your output and using topology optimization to get there. I think it's important for Alex and for Jordan and the other participants as well that you can use the stiffness simulation and the modal analysis to make your design even better, right? And you talked about garbage in, garbage out.
Yep.
When we do these simulations, our topology optimization or our design that we think is great may be garbage. And
Yep.
the benefit of looking at something like Discovery or an FEA analysis is it shows you where these bendings or these modes are. And then you can go in as a designer and as an engineer and add additional support to those areas. And as you eliminate, those bending moments, or as you eliminate where those modes are focused, you're going to make your structure overall less resonant. You're going to make it stronger. And so it's not you design once and then you put it into this and say, yep, we're done. It can really be an iterative process.
Exactly. Yep.
And should be.
Yep. Agreed.
Yeah, let me pull on that thread too a little bit, Garrett. I think it's really important to think of your system and think of it kind of from a systems engineering approach, right? So if you're looking at modes and modal analysis, if you have matching frequencies, for example, between the rotation in which your propellers are turning and a mode that happens to show up on one of the arms of your structure, you can excite that in a way that maybe your payload becomes unstable. Or maybe if you have a gimbaled camera on the bottom of it, now you lose stability of controllability of your flight system. So it is an iterative process. There's no, I would say, golden ticket out of it, and you really need to think about what are the requirements that you're designing to, what are the needs of the process, and how do you incorporate kind of that systems level approach to your design methodology, and know that it's okay if you have to go in and design and redo. We do it all the time, and this is definitely an iterative type discipline. So the trick is getting into the art of learning how to do that and where to apply more mass or more material, or change shapes and so forth.
To tug on that one more time, it shows you maybe where your most susceptible areas are, but it also shows you by not showing you where your strongest areas are. And maybe that's a great spot to pull out mass. Every time you add stiffness to these high frequency trouble areas or these low stiffness areas, you're adding mass. And obviously part of this with a drone is stiffness to weight. And so if you can add stiffness and by extension add mass to these areas that are maybe more troublesome, you can also pull mass from these areas that aren't as big of a concern.
Yep. No, great point.
Okay. I'm going to go ahead and pause the recording, and then we will let everyone ask questions.